Hi, I'm Josh Benabou, and I'd like to tell you about our paper, Axion Mass Prediction from Adaptive Mesh Refinement Cosmological Lattice Simulations. This is work with Malte Buschmann, Josh Foster, and Ben Safdi. In our work, we compute the value of the QCD axion mass that gives the correct relic abundance of dark matter, assuming as a UV completion a field theory construction with domain wall number 1, and further supposing a post-inflationary cosmological history for the axion. In field theory constructions, the axion arises as the Goldstone boson of a global U1 Peccei-Quinn symmetry broken at some high scale Fa. It is described by a Lagrangian of the type shown here, where the axion is identified as the phase of this complex scalar field phi, the PQ field. If the Peccei-Quinn symmetry breaks after inflation, then we generically obtain axion-strings. These are one-dimensional topological defects of the PQ field, characterized by the property that on any path encircling a string, the axion has a non-zero winding number. After the PQ symmetry breaking phase transition, axion strings form, and as the universe continues to expand, the strings emit axions. Eventually, this network of strings enters the so-called scaling regime, where the string length per horizon, psi, becomes approximately constant in time. The QCD axions which are radiated by the strings eventually become non-relativistic and contribute to the dark matter abundance. If the domain wall number is 1 and the QCD axion is the dark matter, then there's a unique value of the axion mass that gives the correct relic abundance of dark matter. To compute this value, we solve the classical equations of motion of the PQ field on the lattice. We evolve our string network through the PQ breaking phase transition and into the scaling regime. And to capture the large hierarchy of scales between the width of the string, which is set by Fa, and the cosmological distances over which the strings move, which is set by a Hubble length, we use the technique of adaptive mesh refinement. This allows us to reach well into the scaling regime to the point where the log of the radial mode mass divided by Hubble is equal to 9.75. Without AMR, this would require a static lattice simulation on a grid of size approximately 260,000 cube sites. We performed our simulation on the NERSC supercomputers Perlmutter and Cori using over 25 million CPU hours. In our simulations, we find evidence for the growth of the string density parameter xi as a function of log of mr over h, consistent with other works. Our precision measurement of the attractor solution allows us to extrapolate xi all the way to the QCD phase transition, at which point we find it should lie roughly in the range between 11 and 15. Further, we measure the energy emission spectrum of axions in our simulation and find that it is scale invariant to within 1% precision. This is in tension with some other works which find that the spectral index of emission should grow logarithmically in time. On the other hand, we demonstrate explicitly that a growing index may be explained as a biasing effect arising in the fitting of our spectrum to a power law if the UV cutoff assumed in the fit is too large. In addition to our simulation in the scaling regime, we perform an additional simulation to study the dynamics of the string network through the QCD phase transition. QCD induces a potential for the axion, which explicitly breaks the U1 PQ symmetry and causes the formation of domain walls which collapse the network at the QCD phase transition. If we account for axion production only prior to the QCD phase transition, then we predict that the axion mass should lie roughly between 40 and 70 microeV. However, in our work, we provide preliminary evidence that axions should be emitted through axions emitted during the collapse of the network may actually dominate the relic abundance. This would potentially increase the mass prediction up to as much as 300 microeV. In summary, in our work suggests that the QCD axion mass lies roughly in the range between 40 and 300 microeV to explain the correct dark matter abundance. QCD axions in this mass range can be probed by future experiments, including MAD-MAX and ALPHA. On the other hand, our results are subject to a large systematic uncertainty due to our only approximate accounting of emission from domain walls, which we found could dominate the dark matter abundance, though this should be studied in more detail in a future work. Thank you for listening, and we hope that you'll check out the paper.